Okay, linearization. So previously we talked about Laplace transform and about transfer functions. Now we want to talk about linearization. Why do we care about linearization? I'm pretty sure in other courses you have studied linearization, the idea behind linearization, you have heard about it. Uh, so why do we care about these things? Because right now we are focused on transfer functions, and as we previously discussed, transfer functions are only defined for linear systems. Not only they are only defined for linear systems, they are only defined for linear time invariant systems. So what we do if we do not have a linear system, if we have a nonlinear system, is that we find a linear approximation of that nonlinear system near the point of linearization. Okay, so uh, what do I mean? The behavior of some systems, for example, a pendulum, is nonlinear. So when we study them, we say, okay, you know what? I don't want to talk about the entire behavior of this pendulum. I only care about a specific point, a specific position that the pendulum is located at. I'm pretty sure you all remember that we have studied that previously. We are going to see some examples today. Okay, so what's a linear system? A system is linear if it has the following two properties. Before I start talking about them, notice that we are talking about a system being linear. We are not talking about a function being a linear function or a function describing a line. We are talking about a system being linear. We are going to see the difference. Okay, so a system is linear if it has two properties. One, being homogeneous, which means that if you scale the input, the output is being scaled. So I give my system a function of time and it's producing another function of time. If I scale that function of time here u, then the output would be scaled too. For example, I give a sinusoid, let's say sine of 3 times t to my function, and the output is something, it's like 5, the number 5. If I make my sine of 3 times t twice as big, so if I make it 2 times sine of 3 times t, that the number that was appearing in the output should become double if I have doubled the sine. So if I scale a function or the input function to a system, the output should be scaled too. The second property is superposition. If I have input number 1, which produces output number 1, and I have input number 2, which produces output number 2, if I add them up and feed them to the same system, the output is going to be output number 1 plus output number 2. We have seen this before in other courses. For example, if you have a circuit and if I know that if my battery, the voltage supply that the battery is supplying is 1 volts, and I'm measuring the current or voltage of something in that linear circuit, and if 5 volts in is producing, let's say, 12 volts out. If I make the input twice, if I make 10 volts in, I expect to get twice as big of an output. So if the output is 12 volts, I expect to be 24 volts. That's uh, being homogeneous. But now for superposition, if I have the same circuit and if I'm giving it 2 volts and it's producing, say, 12 volts, and if I give it 1 volt, it's producing, let's say, 6 volts. If I give it 3 volts, which is input 1 plus input 2, I expect to get output 1 plus output 2, so 12 plus 6, which is 18. Okay, now that's a linear system. What's a linear time invariant system. A linear time invariant system is a system that, in addition to previous properties, which we're describing how to be linear, it is time invariant and it is causal. Time invariance means that if you have delay in your input, the output would be delayed too. So imagine I'm giving some input to my system and it's producing a specific output. If I come back tomorrow and give it the same input, it's supposed to produce the same output tomorrow. If I apply the same input 10 minutes later, so with a delay, I give the same input, it's going to exactly produce the same output delayed. And causality means that the future doesn't affect the past. It's a concept that for physical systems, it's always satisfied. So I'm not going to really talk about it as much, but it's more kind of a mathematical concept. All right. So let's see these examples. I have the following four systems, and I want to determine whether or not they're linear. So is this linear? Is this linear? Is this differential equation describing a linear system, and whether or not this is linear, right? So 2x. I want to see if function f1 equals to 2x can describe a linear system if this is the dynamics. This is describing the dynamics of my system. So if I describe my system as a system with x being the input and f being the output, well, if x is the input and f is the output, and I want to check linearity, I can check to see if it's scalable and if superposition holds. So if I make my input x 8 times bigger and check if f of ax is equal to 8 times f of x, that means that it's scalable. And this is superposition. If f of x1 plus x2 is equal to f of x1 plus f of x2. For a system that its dynamics can be described with this equation, both of these properties hold. F of x1 plus x2 would be 2 times x1 plus x2, which I can then distribute 2, and I write it as 2x1 plus 2x2. 2x1 would be f of x1, 2x2 would be f of x2. Also, if I have if I have f of ax, this would be 2ax, which can be written as a times 2x, which is a of aifx. Okay, so this is describing a linear system. How about a system which has, I can describe the dynamics as ax plus b. Well, let's see if it's a homogeneous system. F of x1 plus x2 would be this should be a times x1 plus x2 plus b, which then I can multiply. It's going to be kx1 plus kx2 plus b. But the problem is that it's not going to be equal to f of x1 plus f of x2. Why? Because f of x1 plus x2 is going to have this b here, but f of x1 plus f of x2 would be kx1 plus b, and f of x2 would be kx2 plus b. If I add them up, I'm going to have kx1 plus x2 plus 2b, not b. And therefore, the system is not linear. So this is a line. The equation that is describing this system's dynamics or behavior is a line. But the system is not linear. There's a difference between a linear system and having a line as the dynamics. Okay? How about this system? I have a system with this differential equation being its transfer function, being the describing the dynamics. It does satisfy the superposition. You can replace x with ax, and also you can check it's homogeneous. It also satisfies the other two additional conditions of time invariance and causality. So this system And in general, every ordinary differential equation that we study are linear and time invariant. That's why we engineers care about ODEs, ordinary differential equations, so much, because they are a very, very special case of equations that exist, and they are describing the behavior of systems in time that is very, very, I guess, small portion of systems. It's systems that are linear and they are time invariant. How about this last system? Uh, this system is not linear because it has a sign in it. So if I try to scale x4, if I write 2 times x4 here inside, it's going to be sine of 2x4, which I can't bring 2 out. I can write 2 times sine of x4. So it's not scalable, and it's not homogeneous, and it's not describing a linear system. Okay. If I have a nonlinear system, as all of us have studied in other courses, we can linearize the equations. We can find a linear approximation. We have Taylor series, and we have other series that we have studied. The equation for Taylor series is this. You have a function, it's nonlinear. I want to find the linear approximation of it close to a or in the vicinity of a specific point. Obviously, you can't estimate a nonlinear thing with linear thing, or a nonlinear function with a linear function. You have to find an approximation around a specific point. So this is the point that we care about. If it's x naught, the linear approximation of g would be g of x naught plus dg to dx of x naught, being evaluated at x naught, times x minus x naught divided by 1 factorial, and then higher order terms. Okay. Now let's see a linear approximation for a pendulum. Do you remember from labs in physics courses and previously, we were always, when we were in the lab, told that if you're working with a pendulum, move the pendulum uh, just a little bit. Like this angle should be, I remember they would tell us to move this angle or move the pendulum in a way that the displacement is creating an angle less than 6 degrees, right? So that is what linear approximation means. We were trying to have a linear behavior out of this nonlinear system. And for that, we would approximate the behavior near a specific theta, which was theta equals to 0. So now let's see equations here. So if I write the differential equation of this system, I have t equals to m times g times L times sine of theta. M is mass, g is gravity, L is the length of pendulum here, theta is the displacement, and T is the torque, okay? And we are interested in theta 0, which is equal to 0. If I apply Taylor series, what I'm gonna get is this. MGL cosine of 0 times theta minus 0, which is MGL theta. So the linear approximation of MGL sine of theta is MGL times theta. If we are interested in very, very small displacement, or any very small displacement around theta equals to 0. Okay, so that's linearization. Now, this last slide is just an example for the system described by differential equation below. Find transfer function. System at rest means that the initial conditions are all 0. Find the solution if the input is a unit step, and find the step response. Use MATLAB and find output if u equals to 1. I request, I would suggest you to stop the video and think about it, and then we have the solution provided.